start on time since the room's already full. So it's a pleasure to welcome Shaojie from Hong Kong University of Science and Technology. He got his MS and PhD at UPenn and his bachelor from Hong Kong University of Science in 2009. And since 2014, he's back at Hong Kong University of Science and Technology and leads the DJI Innovation Lab. He does very nice work in state estimation, perception, navigation, and has received numerous best paper awards. It's a pleasure to welcome Shaojie.
Yeah. Yeah, thanks, Chen. Okay, I guess first, sorry for my voice. It really get destroyed for unknown reason. I don't know what. And actually today after meetings with so many colleagues, I get practice my voice up a little bit. So, but it may not be the best performance. And in case you have issue understand what I'm talking about, and just feel free to stop me at any time. So it's really my honor to come here to the top place in robotics to talk about our recent work on visual perception and navigation for consumer drone. Okay, so probably start with some very brief intro about myself. I get my PhD from a nearby place, UPenn, 2014, and after that, just go back to Hong Kong and start up the aerial robotics lab over there. And we have very close relationship with DJI, and I also see many of the DJI drones inside the place. And so I do my research basically focus on autonomous navigation of drones using different sensors. And basically try to make it as safe and low cost as possible. Okay, so I want to start this discussion with just a discussion of trend of consumer drones. Okay, I know there's another line of professional drones that tend to be bigger, longer flight time, but today's talk I will mostly be talking about what on the consumer side, on a relatively lower entry barrier side, the drone will look like. Okay. So Phantom, probably many of you have heard about it, and which comes somewhere between 2012 to 2016, and then until like Phantom 4 that has a weight of 1.1 kilogram. The Mavic series, 700 gram. Spark, even smaller, 350 gram. Well, you can get here and there the toy drones that is about the weight of 50 grams. They're not technically drones, they're just like RC toys, but hopefully at some point if you really want to make a drone that can fly, for example, in swarm, or can really navigate through very tight space, that might be the size to go. But we also face a lot of challenges. Okay, so basically we see the trend of at least one direction of where the drones are heading for is they tend to be smaller, low cost, portable, but it also have a very strong implication that it has to be safe because people tend to use this kind of drone in a very narrow space that probably filled with human, filled with man-made structures, small obstacles or moving structures. So that poses the problem of how can we make safe small drones. Okay, so that's along the main line of my research. It's basically subject to many constraints like limited payload, limited size, limited budget, and close proximity of obstacles. Okay, so to solve the problem, we first basically just start from the sensing side. Again, many constraints, has to be lightweight, has to able to support real-time operations. You cannot just stream all the data back to the cloud server and get it back. It basically doesn't work. It needs mapping. But it actually needs a very dense map of the environment to see even the smallest obstacle available. It needs metric distance measurements. So not like, for example, use a monocular camera where you see things, you detect things, but if you don't know how far things are, you're still not able to do a good job with it. And it should also be able to handle dynamic environments, meaning that even though there are things that moving around, it should still survive. Okay, So we start off by eliminating a number of choices, like later first cut it out because it's too heavy. We may also use multiple pairs of stereo cameras to perform the state estimation and obstacle detection mapping. Also cut it out for now because stereo, you always have the baseline requirement that if the size shrinks down, everything becomes monocular. A stereo basically will not have that much effect because of the stereo measurement distance tend to be very, very small. Active time-of-flight sensors like the Kinect or RealSense, they tend to be able to give range measurements relatively good indoor, but for outdoor scenarios, the performance tend to be a little bit bad. So again, cut it out. And at the end, the only thing left is, okay, I cannot use many cameras. How about I just stay with one monocular camera? And on pretty much all of the consumer drone, on all of the drone, we always guarantee to have an IMU that's on it. So we're actually looking into a monocular visual-inertial system. Pretty much is what is widely available on all the cell phone. So cell phone has the IMU that you can play games, but it also have, also have the one camera, they take pictures. It actually turns out we can use this thing to pretty much solve all the navigation requirement for a drone's task. And it's pretty easy to think about it as a very lightweight sensor and very low cost, definitely. And if we can do a good job on the navigation performance, that actually provides a possibility to solve the full problem. And in the title, I had the word of minimalist perception. So it does not mean a bad perception. It does not mean that I just, for example, just want to do optical flow and try to solve all the problem. We actually mean a complete navigation system that satisfies all the sensing requirements. So when we look at the complete navigation system, what does it actually consist? We can say about, at least from the perception standpoint, get into the state estimation, the mapping. So that's well known. And also for the tracking problem. What I mean by tracking is how do you track the 6 degrees of freedom, the 3D motion of moving objects in the environment. Only when all the three are available, then you can call it the system can actually save to navigate in any environment. And if we look at what's the state of the art of the current approaches, I just roughly characterize it as like 3 stages. What's the estimation? I'll call it pretty much a well-solved problem of figuring out what's the ego motion of the platform. Mapping with only one camera, we're getting there, still have some work to do due to various limitations such as the estimation accuracy, the computation complexity, but we're getting there. For tracking, due to the pretty a straightforward constraint that one camera cannot estimate depths, we still have a lot of work to do. Of course, you can survive with only a 2D tracking, but that also poses a limitation as things like you've got to have no idea how fast things are, and you're probably being affected by fake measurements. For example, if it can be confused with a real car and a toy car. Okay, scenario like that. So really, we need more work on these directions. So today, I'm mostly focusing on what's our approaches to deal with all these 3 types of the problems. Okay, so first on the state estimation. So our approach to the state estimation has been the WINS Mono, which we released about a year ago, and it's a fixed leg smoother, sliding window-based visual-inertial, tightly coupled visual-inertial fusion methods, and it's open source on GitHub. Has already received like 1,000 something stars that you can try to play around with it. So the system diagram looks like this. Looks rather complex, but it basically being decoupled into a few system blocks. First is where the measurement pre-processing. That's how we do the feature-based method. Yes, we still do the very old school feature-based methods, no learning, no direct methods. And even the feature tracking has been a very, like 30 years ago technology of KLT tracking. But it turns out, even with a very simple front end, we can reach a fairly good result. spend a lot of effort in IMU processing, on IMU pre-integration and IMU correction, bias correction, and have a dedicated module for initialization. That's a unique feature, unique requirement for monocular system that with just using the cameras, you have no idea how fast things are, and we do need a dedicated initialization procedure to get the scale of the system out and also get attitude measurement that is aligned to the gravity of the Earth. And the central of the system is a visual-inertial bundle adjustment with relocalization. That's the middle block over here. We also have loop closure and post-graph optimization to eliminate the drift. Okay, so the central part is essentially visual-inertial odometry with relocalization. We already focus on the local accuracy, which is, for example, like the range of measurement for plus and minus 100 meters around in this range. And we actually aims for a sub-centimeter accuracy, even for example, for indoor environment like this, should reach accuracy of somewhere between 2 to 3 millimeters. And that actually serves as the foundation for many of the subsequent tasks. And again, for those of you that come in late, my voice gets destroyed for some unknown reason. So if you cannot understand very clearly, just feel free to stop me at any point. Okay, so and we aim to already provide a relatively flexible system that have many built-in features on it, such as estimated initialization, rolling shutter compensation, bias correction, temporal and extrinsic calibration. So basically, you want to really get to a situation that you just plug 2 random sensors on it, and then it should be able to work. Of course, things doesn't really always work that way, but we always try to push through in these directions. Relocalization is what really helped to such that the system can recover after failure, and we consider it's as a sensor fusion problem, mostly by how to combine the 2 sensors together. And it actually shows a very significant effect, very good, very positive effect in this scenario that it significantly increased the robustness compared with, for example, just vision-based method like ORB/SLAM also. And the current framework, we can easily add more sensors. I'll illustrate later. The post-graph module, it has been pretty straightforward, but we make use of many of the front-end situations that we actually support multi-constraint loop closure constraints being integrated into the graph, and we can support tightly coupled relocalization, meaning that not on the relative post-transformation level, but actually on the feature level to do the relocalization. And again, from the engineering perspective, try to make the system easy to use. So we already have the map save and loading mechanism and post-graph merging mechanism, such that we can reuse information that is available previously. Okay, so that's just one video showing the results. So the EURC dataset, many of you should have already should be pretty familiarized with this, and we basically use the 1 camera on the EURC dataset, and just keep running. You're loading all the sub datasets over there, and it actually turns out to be used a system by just keep pressing the enter button. We can pretty straightforwardly merge all the trajectories of the single dataset altogether, and there's no failure with the monocular system, and we don't need a dedicated initialization procedure. So basically, it just takes off, and then everything can be merged on the same map. Okay, the map itself doesn't really make too much sense. It's just some random trajectories, but it can help to eliminate the drift by doing relocalization on it. Okay, so that's a result. And also run the same thing on a campus setting. That's our HKUST campus, slightly larger scale outdoor situation that we can just run multiple trials of data sets, and the system will be automatically able to merge all the trials together whenever it actually detects a loop closure. And yeah, again, just a convenient feature for you to use. Okay, I'll just jump through it. And recently, we also have an upgraded version of this WINS mono, or we call the WINS Fusion. released last week. And we basically add in stereo support, wheel odometer support, and GPS support on it, such that it can actually run on the Kitty dataset, which don't have asynchronized IMU data. And so far, I think it's on the Kitty stereo odometry benchmark. We are the top one on it. And the good thing about using a similar framework on this situation is that the system can be actually robust against sensor failures, in the sense that now it can work with monocular camera, stereo camera, monocular visual inertial, stereo visual inertial, and plus or minus odometer and wheel support. And pretty much at any point, as long as the system have more than one sensor available, it will survive. Like with a stereo system, and even if one of the camera fail, it automatically switch to the monocular case. And with a monocular visual inertial system, that for example, even at some point, if the IMU jumps up, and it will automatically switch to the stereo configuration. It's not technically really a switching, but it's more like fusion mechanism. So it's just like the information that is being pulled into the sliding window bundle adjustment will be less. Okay, by using that, we actually created a fairly usable benchmark for a lot of the state estimation tasks, either on a ground vehicle, on aerial vehicle, and some of our colleagues also have used it on surface vehicle, on boats. Okay, and it also just open source last week, and for those that are interested, we can try. There might be still a lot of bug in it, so we are actively adjusting the feedback from other researchers. Okay, so that's the state estimation part. After we get a fairly reasonable ego motion estimation, the next question really is how do we build up a map such that the robot is able to navigate safely inside a complex environment. By building a map, we pose a number of system design considerations. First thing first is, should we do joint optimization of the map and the pose? And our selection is no. So we build a map condition on the state estimation result instead of doing like a joint dense bundle adjustment due to computation constraint and also the engineering constraint that the pose, at least for now, is fairly good enough. And basically it's conditioned on the feature-based visual inertial state estimator that I present thereafter. So, so it's a multi-wheel motion stereo, and we spend a lot of efforts in parallelization on GPU and others of method to improve the performance. So there are many techniques to do dense mapping with only monocular camera, but basically we can characterize the system that consists of, for example, these following blocks. Sorry. So again, that's non-camera pose, so it's not SLAM, it's only the mapping process. So if we look at steps, given a sequence of input images, we first construct a cost volume by comparing the similarity between pixels in a reference image and a measurement image, multiple image, compare the similarity, and then get a cost volume. And the second step is ready to extract the depth image from the cost volume using different optimization techniques. You can either go for a simplest winner-takes-all, some sort of local smoothing, semi-global block matching, pre-propagation, variational method, or learning-based method. So there can be different methods that try to serve the second steps. And the last step is to fuse a depth image, multiple depth image into a spatial map. That is what's really useful for navigation purpose and filter out all the noise for the depth images. So when we look at the challenges involved there, of course, first thing first, wherever things that involve dense image, we always have the computational burden out of it. And we also have issues of handling the complex environment, such as textureless vision, reflective vision, fine structures, thin structures, and that can be hard to deal with handcraft optimization-based method. We also have the issues, challenges of mapping large-scale environments, large-scale spatial maps. So our solution to this is actually 3 different works. First is to reduce the number of pixels to be processed using a quadtree-based representation. Second is use a learning-based method from cost volume, not from a raw image, due to various reasons. I'll talk about that. And to improve its capability to handling complex environment mapping. And last is server-based depth map fusion to deal with larger scale environments. So let's start with the acceleration method. So we start with the observation that not all pixels in the image are equal. So even though if I want to compute a depth map, we not necessarily need to compute it for each of the pixels. Some of the depths of some of the pixels can be solved in low resolution. For example, those areas that don't have a very strong variation in the depth discontinuity. And we also have the second observation that the quadtree structure on image, which people often use it for image compression or other image processing usage, can be indicate the suitable resolution for the corresponding depth image, in the sense that the quadtree level on the intensity image will be always finer than the ones on the depth image. That's a rough observation. And then to this end, we can use the quadtree representation on the intensity image to do a segmentation. And then after the segmentation, we can selectively reduce the number of pixels to be processed for depth map computation by using a specialized split propagation method that only smooths the pixels up to the quadtree level that they are representing. Okay, and the final result will look something like this. So given an input image, and basically just do a quadtree segmentation out of it, and we can estimate the depth of those pixels and further incorporate into a full depth image in a probabilistic way. And those red things are bad pixels that are far away or no texture whatsoever, so that's being dropped. So that's the real-time running on an NVIDIA TX2, and for an indoor environment using the state estimation from the WINS model. And we have some bad pixels due to, especially during rotation, that the image don't have overlapping. But we can still merge, get a depth image and create a map that is merging all the depths together. It's not the best for sure. The resolution is not high either, but it at least serves as the foundation for obstacle avoidance purpose. And since it's just one camera and it works for both indoor and outdoor compared with the depth sensor, and also it can work for much longer range, because for monocular camera case, the distance I can measure only depending on the baseline, which is motion baseline. So we can adaptively choose the baseline of each of the pixel, such that for pixels that are at longer range, we can choose a very long baseline to increase the depth perception accuracy. We did use for autonomous navigation experiments. So that, again, that's for indoor use, and it's a drone with just one camera in front and custom-built drone indoor in our lab. This is a workshop representation. That's a raw image. That's the only information that the drone takes in, and that's the depth estimation. And basically use that to navigate through relatively cluttered indoor environment. Okay, I'll defer the video to something after when we talk about the planning session. So just jump through that. Okay, the second piece of work that we have here is how do we deal with some of the challenging situation, for example, like the scene structures. Using for example, like semi-global plot matching or other handcraft optimization method, it can be relatively difficult in this scenario. But this kind of scenario can be very good to solve using a learning-based approach. But what we should look at is what to learn and when to start the learning-based approach. Of course, we can just input two of the image together and give it the ground truth and expect the learning-based approach will be able to give a fairly good depth estimation. But we soon find out that by using that approach, the system becomes relatively sensitive to the training data and actually need a lot of real-world training data with the ground truth labeling to get a good result. So to this end, we modify a little bit to do learning-based approach on the cost volume. You remember I talked about, so we compute the image similarity to a cost volume. So we do it on the cost volume rather than on the raw images. And the network structure has been fairly straightforward, but really what makes it different is that after you learn it on cost volume, since it's just image similarity differences, it makes it invariant to camera entrances. It makes it also invariant to camera motions, also invariant to number of images. So to this context, the system can become much more robust and also even get to a point that it can be trained with simulator data and apply into real-world situations. Okay, so that's some of the video that we have. So again, maybe from the video cannot really see so much of a difference, but when we actually doing a quantitative comparison, we see we saw improvement, especially on scene structure or textureless region. The others are, this is another image-based, another learning-based approach, and the others are handcraft method that sometimes use artifacts for the multiple path or semi-global matching, or other issues with the depth filter-based methods. Okay, so that's just another line of our work to try to make the depth extraction better. And finally, after getting all the depth information, we want to actually fuse them all together into a globally consistent representation that we can use for navigation purpose. Of course, we can just create a grid map to fuse everything together, but at some point that makes it prohibitively difficult in terms of both memory and computation complexity. So to this end, we basically just turn to a servo-based method. Again, approximation of the information using servos that will reduce its density, but it has the advantage of very fast computation and lightweight, and able to handle relatively large-scale environments. So again, that's just a kitty data set. And the good thing about using servo-based compared with volumetric is that it's naturally able to handle loop closures. And then we actually maintain a graph that it can extract relevant information immediately after loop closure, things like basically the map that is extracted before in the previous loop, that can immediately use all the relevant local information for the planning purpose. So this is running on a kitty data set that is relatively large scale, but the whole system is able to run in real time while extracting all the local map information for obstacle avoidance on a scale of millisecond. Okay, so that's some of the maps. So basically the robot is here, it always maintain a map in its neighborhood regions. So again, the map is not the best for human perception perspective, but we have successfully using that for drone obstacle navigation purpose, which requires significantly less resolution on it. Okay, so after the second step, we make it fairly confident of flying in static environment, even using one camera. But then the problem remains is that what if the environment actually have moving objects? So two types of moving object. One is that if you have moving object that you want to track. The other is if you have moving object that you don't want to collide into. Okay, so the problem here is actually how do you know what's the 3D motion, the 3D location of the moving objects. So if we go back to look at the drones, not the monocular ones that I'm mentioning, but if just look like a DJI Phantom, it uses the main camera to track the object, meaning that it can do a 2D tracking, but have no idea how far things are. Okay, that's a common problem of monocular features. So when you don't know how far things are, the tracking becomes a little bit tricky as your control loss becomes ill-posed image-based visual servoing. That's depending on the dynamics of the object, it can be very, very hard to control a precise following. So our goal is really to try to find a way to figure out how far things are. So figuring out what's the direction of the thing of the object is not hard. You can use existing 2D-based image tracking method, detection and tracking method to solve the problem. But for finding out how far things are with only one camera becomes a little bit tricky. So our goal is to develop a geometric-based approach to estimate the 6 degree of freedom pose of dynamic objects using monocular visual information. We condition on the sense that it only requires a 2D tracker, meaning that it don't need a 3D detector over there, and it should work on any rigid objects, meaning that even though if it is something that you don't know what it is, you're not able to figure out its 3D pose, but as long as you can track it, meaning that you have reasonable texture on it, you should be able to find out the distance of these particular objects. Okay, so let's look at the problem formulation. So first of all, even with one camera, the camera trajectory can be easily obtained by monocular visual-inertial state estimation. That's not a big problem. But and the second, if you have a 2D tracker, you can always perform a local bundle adjustment on the object to obtain the relative motion of the camera with respect to the object, and also obtain a point cloud on the object. Basically, it's like slam on the object, assuming that it's not moving. Okay, but of course, since you only have one camera, that's going to be up to scale. So the problem really is to, if you just look at this equation, that's just a geometric transformation. For things with a bar on it, there's up to scale info. This has the scale information. But what you really is need to estimate the scale such that the equation holds. W is the world frame, O is object frame. That's what you want to estimate, the object pose in the world frame. Okay, so you need to estimate this scale information in order to obtain a metric object pose. So again, the challenge is that the metric scale of the object is not directly observable. And of course, to deal with this unobservable feature, we may impose additional environment-specific constraint on the object. For example, if you know what the object is, you know that it's a car, you know rough size of the car, then you have an idea how far things are, right? But this does not solve all the problem. For example, what if someone just use a car with different size, a small model car, to just kind of attack your algorithm, that you actually tend to mess things up. And we have human detectors but we have different heights. If we compare a basketball player with a kid, that might also mess things up. And it actually turns out that that is very, very dangerous for a drone following situation. That if you use the same control law for a very tall person and on a kid, that tend to be significantly reduce the control performance of the drones. Okay, so we actually want to design a system that does not require on the additional environment-specific constraints. So our observation is really that the camera motion and object motion are statistically uncorrelated, meaning that, okay, they're two things. They move on their own. They're not, most of the time, they're not anything that, for example, move in parallel. They're not coordinating. They're statistically uncorrelated. So now the problem becomes estimate a scale parameter, that S, such that the camera motion and the estimate metric object motion are statistically uncorrelated, meaning that you pretty much like decoupling this thing into two trajectories, while you know one, and that you want the other one to be statistically uncorrelated to the one that you know. Okay, and using this mechanism, we can actually separate the motions and creating something that is metrically correct. Okay, so I won't go into details on here. The work is being published in in last year's IROS. And also pending publication for TRO. Okay, so just I use a video to illustrate its working scenario. Okay, so the whole system starts with a 2D object tracker. This existing one like YOLO. I'm not doing any object track. Okay, like use YOLO for detection and just, for example, just use a correlation filter for tracking. And so that's the input image. That's the 2D tracker. And I don't know whether you can see there's a small point cloud over here. That's the camera motion with respect to the object. So the object itself is not moving. And this is the camera motion, the red one in the world frame. The green one and the green point cloud, that's the object itself. And the blue one, that's the object trajectory under the motion capture system. That's ground truth. So we can actually see that the metric scale of the object motion is actually correct, despite the system actually have no idea what the size of this car as a prior. And it cannot use any 3D learning-based method to infer the object size because of the size of this car is not the size of a real car. Okay. I can further and the whole system works in 3D, so even though it moves up and down, and then it won't have any issue. So to make it more clear, we have, for example, scale ambiguity test. One camera checking 2 Mini Cooper, toy Mini Cooper, but they're actually with different size. And we need to estimate the distance of the object on this scenario. So the thing to verify is that we do an AR situation, that we project an AR axis with 15 centimeters on each onto the image. So if the object size estimation is correct, we should see a different axis compared with the object on the image, right? So that's what you're looking at. And as long as the size of the axis remains accurate and it attached on the object, meaning that the tracking is working. Okay, so more experiments with different objects showing that it can actually work without we knowing what it is. So that's a robot, some bottle, can hold it, and a NVIDIA TX2 board. Yeah, still the same thing. They're all running exactly the same code on a parrot box. Okay, just basically showing that the system is able to work with different objects. Of course, this thing has limitations. Okay, it will fail when the two things are not statistically uncorrelated, especially things like if you have two of the camera and the object to be tracked running in parallel, it will fail. But we do have an analysis of which of the situation will be degenerate, and that's being presented in the paper. Okay, so now let's move to the last piece. After getting the perception requirements, we still have to close the perception and action loop to build a fully autonomous drone system using only the monocular camera and the IMU. And we want to make it that it does not require on prior map information and have all the processing runs on board. Actually, to be honest, after figuring out the post-estimation and the mapping problem, the planning problem becomes sort of independent of the sensor that you're using. So we actually didn't specifically develop a set of sensing system that works with the monocular sensing case, but more like a general sensing approach, general planning approach. But it actually turns out that it also works with the current setup. Okay, so first is the trajectory generation. So our trajectory generation is following the current strengths that we have a series of paper back at 2014 on the trajectory generation methods, and basically decoupled into front-end path searching methods. And so for this particular one, using a fast marching method to generate a path that actually have a velocity profile on it, and a back end for generating constrained and safe dynamically feasible trajectories. So the back end is really how do you generate the trajectories that is based on a flight corridor setting, meaning that how can you fill out the environment with a set of collision-free polyhedrons, and how can you generate the path that is going through all those polyhedrons, and how do you make the things happening as fast as possible, and also to constrain not only the spatial collisions and also the high order dynamics like velocity, acceleration, etc., etc. Okay. And we also have methods to do GPU-based acceleration on how do we extract the polyhedrons to get the free space information. And then the key thing is basically a massively parallel implementation of raycasting that basically able to fill up the space on a grid setting that it can compute fast on GPUs. And the good thing is that the computation onto the polyhedron generation is on the same map that the mapping algorithm is able to find, such that everything can be that we can reduce at least one or even more memory copying between CPUs and GPUs. And that's some of the results that have like fill up the space with collision-free polyhedrons and generate a path across it. Okay, so again, just go for some of the videos. So it's again the monocular camera case, and that's a indoor environment using the same state estimation and the mapping method that I presented previously, and have a real-time running mapping system or planning system on board. So that's indoor autonomous flight in a relatively cluttered environment, and the system also works in 3D, so you can also go underneath the bridge, and all these maps are being generated in real time. Yeah, forget about that drawing. So the average computing time is on the order of millisecond, and the overall latency of the whole system is less than 150 milliseconds. So it also works for the outdoor setting, that on tree branches, without special modification on the code. Okay, so yeah, so able to avoid the thin trees using the monocular camera sensing. Just speed up a little bit. It's just on some mixed indoor and outdoor setting, and with trees around. And basically just have tried an experiment with different situations. That's a normal courtyard that we find in Hong Kong with a lot of tree branches around. So we actually show it to be fairly reliable even for the monocular case. And one thing that at least in our lab we find out is that we haven't put so much effort on the stereo case, and we actually find out at some point when I asked my student to use actual physical stereo system to do the work, they say that, okay, I use a monocular one, the performance is actually better for unknown reason. Okay. Okay, so that's the trajectory generation and planning and navigation in unknown environment after putting up all those mapping component and state estimation component together. That is safe to navigate in a complex space. And the last piece of work that I want to mention is just recently being accepted by IL, and is more like in a teach and repeat setting. So the problem that originally that we start with this work is that we want to have autonomous drone in a drone racing situation that actually beat a human pilot. How do we actually deal with it? There are also a learning-based method that try to ask the drone to interactively steering its control actions through different obstacles, but we try to look at the problem in a different way. Basically, we try to cast the problem of teach and repeat as a trajectory generation problem. And basically, we try to find a trajectories that is topologically equivalent as the human demonstration. And we require the trajectory to be adjustable in terms of the aggressiveness, meaning that actually have a knot that can turn the time, how much time you want to spend on the trajectory. And we also require that the entire trajectory to be smooth. So even though the human demonstration can be very jerky, very non-smooth, the final trajectory should be smooth and easy to execute by the robot. Okay, so just use a scenario to illustrate the system working in action. So for example, this is a path that the human pilot actually did. It looks very jerky, but it's actually a very common case for human piloting inside cluttered environment that you go back and forth a lot. And what we really need to do is to find out the equivalent topology of this graph and fill it with appropriate polyhedron to fill up the space, and at the end to generate a smooth path that is topologically equivalent to the human trajectory, but at the same time is smooth and easy to execute for the drones. Some experiment results to look at. So in this figure, the purple one, that's a human pilot trajectory. Even in a simulated environment, that's what a human can do. For example, like going through the obstacles. So humans tend to be just going here and there a lot to make sure that it doesn't collide. And the blue one is a trajectory that is generated by online trajectory generation that is much smoother than a human pilot. To zoom in a little bit, that's what you can see. So like the human pilot goes this way and the robot just goes straight. And the trajectory of the whole system can actually be turned, meaning that you can go either fast or slow as you wish. Okay, so just a video illustrating is the system in action. Again, a monocular camera case. First, just look at a simulated case. On this one, that's a human pilot just moving around with a jerky trajectory, and on the right, that's a drone that is doing an autonomous trajectory tracking using the trajectory that is converted from the human pilot. In this case, it's going through the same amount of obstacles, meaning that it will pass the game rule, but it's running at a much smoother and faster speed. So I guess for the simulation, probably it's not that easy to see. So let's move to some real-world experiment. Okay. That's a typical drone racing scenario. We don't actually have a good pilot, so you just have someone hand-holding it. Yeah, that's the teaching trajectory. Yeah, and that's a robot how actually fly it. Yeah, it's a terrible teacher, not even able to fly it. Okay, so this is some comparison with, that's the best pilot in our lab, but still just crashed many times. And this is the trajectory being executed by the robot for different speed. We can have a knot to turn the speed. I know it's a not fair comparison. We can definitely hire a better pilot. So and that's also more like an inspection scenario that we start off with a human inspection, such that the drone knows where to go, but the trajectory will be very jerky. Then after that, it converted into a smooth trajectory for faster inspection purpose. And actually it turns out that that's a kind of the mode of operation that an industrial drone inspection may actually need. So again, for outdoor environment, that's your teaching trajectories. That's very jerky. And then this is the drone that is able to execute. And also the speed can be turned over there. So that's our approach of try to enable a drone to drive as good as human, in the sense that we try to make the drone to go better than try to make the drone to do a good job even with the dumbest human demonstration, meaning that you just use your hand to carry the drone to move forward. Okay, so that's the last piece of the work that I want to present. And just to give a quick summary, so my research has been focusing on aerial navigation in complex environment using low-cost sensor, and has presented multiple pieces of work from state estimation to dense mapping to handling of dynamic environments, and also how to close the perception action loop. And then the last piece is really try to combine all the system together to make sure that the system performance, noise, latency, calibration, and implementation issue can all be addressed. Of course, there are many other work that need to do. For example, like the teach and repeat. You don't have online obstacle avoidance yet. How can we actually incorporate online obstacle avoidance while still maintain the speed? And we actually haven't put the dynamic environment handling into the planning loop, and that's also the next phase that we need to do. And also more on the state estimation purpose, and how do we deal with other sensor choice? How can we deal with more challenging environment? So still a lot of work to do. But that's the thing that I want to share about, and thanks for listening to my talk. Yeah.
For the part you were talking about last with the teach and repeat,
Yeah.
does the initial trajectory, is that as necessary as kind of like the box free space that's generated? Because like if you have your teach pattern, you can select a set of boxes and it would generate trajectories through that.
Yeah, that also work. Yeah. Well, we just basically think about a more challenging situation that you have to have someone randomly moving. It kind of need the algorithm need to understand the intention of the human, of that being the topological equivalent. That's what we extract from the drone racing and the inspection type of applications. Yeah, but doing a few waypoints is definitely doable. Yeah. Yeah.
Could you elaborate on the cost volume for the depth perception framework?
Yeah.
Like, what was the cost volume that you chose?
Okay.
Was it like census or something?
Yeah, well, it's just basically like the for specific pixel, the similarities compare from one image to another image, the similarities across different depths. So x, y, that's the image dimension. The third dimension is just similarity across different depths. The same as the cost volume that you use for standard stereo matching base. It's just like a little bit generalized such that it works with the multi-wheel stereo case. Yeah, and for the learning-based method, we use the cost volume is just a intensity difference, nothing special, and then we learn the depth image, learn to extract the depths from a collection of intensity difference, basically.
What was the main reason behind not jointly optimizing the pose and the map?
Okay, so
what was the main reason behind not jointly optimizing the pose and the map?
okay, so basically the map is a dense one, and we had also I sort of constrained myself to the monocular case, making it even more difficult as you don't have a reasonable initial guess of the depths. RGBD can be a little bit easier. So really, to not jointly optimize it is due to two reasons. One is computation complexity. It's like if each of the pixel is kind of correlated in the optimization problem with the pose and other depths, the thing can quickly get out of control. Of course, you can use other dimensionality reduction method to make it better. That's one of the reasons. And the other reason is yeah, so sorry about that. Yeah, and the other reason is that more like a convergence issue. You jointly optimize a dense pixel, meaning that is more like a direct method, directly operating on the intensity image domain. That the convergence region can be very small. That in this case, if you don't have a good initial guess, the system tend to very hard to converge. Yeah, so, and particularly for monocular case, getting a good initial value is very hard, so we just go away with that. And lastly, for the engineering consideration is that if the pose is sort of good enough, and all we need is just getting a map for obstacle avoidance, so we can just get away with using a known pose, and then it works reasonably well.
So there's this intuition that when you have a monocular camera pointed towards your direction of motion, then you just don't have much optical flow in that direction.
Yeah.
In the focus of expansion. So this is, I mean, the results you're getting are actually quite stunning in that despite that specific thing, you don't have your cameras oriented away from your the degree of motion, you still get such high degree of odometry. You have some intuition on why this works as well as it does?
Yeah.
When there's so little signal there.
Yeah, I think it's like two things. Like first, for the odometry, that's not a issue because we basically use measurements on the other places. So not necessarily need to use the forward motion direction. So if you have a wide field of view camera, odometry you can just use the surrounding information. For depth map, yes. If you're just directly moving forward, this point you cannot have the depth, but for nearby you have it. And since you don't have the optical flow on it, you actually notice that the depth here, basically you don't have the baseline. You notice that the depth here is not reliable, and during the planning case, it's actually you can basically when you're closing the control loop, the planner will naturally just avoid that. And once you avoid it, you create a baseline that you're actually able to quickly triangulate the thing out. So I would say if you just like for autonomous driving case, that the robot tend to be driving straight forward, the problem is pretty serious. But when you're using a planning approach, when it's on an autonomous drone and you also plan only in the free space, then the problem sort of disappear because of the coordinated efforts with different modules. Yeah, that's basically how we would explain the situation. Yeah.
It was not very clear to me when you're tracking a dynamic obstacle, if the motions are coordinated, like just going in parallel, why is this a degenerate case? Because you still know the pose of the drone with respect to the environment. So couldn't you just, why is it?
Or because we don't know the size of the object. So this compared with a larger thing, a little bit further away, they look the same. So that's a degenerate case. But if you have the object moving straight forward and the camera looks moving like that, it's sort of okay. That's actually okay. Yeah. Yeah.
I was wondering also for the same research, the dynamic tracking, why the assumption of the rigid body?
Sorry?
There was this assumption on a rigid body, like how well does this translate to like when you're tracking?
Okay, so basically we want to know the up to scale motion with respect to the camera frame, and we do that at its up to scale 3D motion. And we do that with a bundle adjustment on the object. And once you want to do the bundle adjustment on the object, you're basically assuming the object itself is rigid. And we do have a subsequent work that we have special handling on human bodies. And basically, you, for example, use open pose to track the human joints. That you can use this joint as the control point, and then even the joints moving is still okay. But that's only for human. It does not extend to other, like if you have a tower that waving around, it basically still fail. But non-rigid object can be, it's definitely a direction, but at least for now, I don't have a method to deal with it yet. Yeah.
Have you thought about using a rotating camera instead of a fixed one to give more detailed information? Because most DJI phones already have a rotating camera.
Okay, so I would say for rotating camera and wide-angle camera, they're the same thing. At least from a navigation perspective, that you don't need a 4K image. I can just use a fisheye camera to replace the rotating ones. And for 3D perception, a rotating camera won't give you any additional information because rotating won't give you triangulation anyway. So probably just at the end, use a wide angle camera.
Okay. Let's thank
Thanks.